All right, so now that we have a fully working block cipher, I'm going to upload this to GitHub so that anybody who wants to can follow along. And you can see that most of these files are just going to be the leftover build files. So we're just going to remove the build folder. So we can see we have our source file. You can see we have our header. You can see we have our Cha-Cha 20 block test. And we have our test header as well as our CMake. So we can publish this to GitHub and we'll make this public. So this should be able to be followed along with now. So we added the Cha-Cha 20 cipher. And in real time, those videos were about a week ago. I know I said tomorrow, but I got busy with work. So now we need to examine what we have built. So when we're looking at a cipher like this, or any kind of really formally developed software, there's a couple of aspects that we're going to want to keep in mind. The first is there is the algorithm itself. So we've got Cha-Cha 20. Then we have our implementation. Or well, I suppose we could look at this as we have the language it's implemented in and any properties that that language imparts. So C's, we'll call them sharp edges. And then of course there's what our implementation allows callers to do. So usually I like to start with the theoretic. We want to look at the limitations of the algorithm that we're implementing before we go ahead and look at our implementation. So with Cha-Cha 20, there's a couple of things. That's probably better typed. So the first is remember that the same key and the same nonce will lead to issues. So key plus nonce is the key stream, and this needs to be unique. If we don't use it uniquely, you can XOR two ciphertexts together and that can expose relationships between the plain texts. So that would be bad. The second thing, if we go back up here, so we have our counter and our state matrix, right? And our counter is a 32-bit word or a 32-bit counter because of that. So we have 32 bits. We have 32 bits. And this, we can't let it wrap, because if it wraps back around, it starts back at 0. So if, you have your counters like this, and these all start at 0, and then, you keep going, you have 1, and then 1, and then you get full, and these are all 1s, then you're going to roll back to 0. And at 0, we would reuse the key stream for the same key and nonce. So we can't allow that to happen. So basically that gives us an upper theoretic limit on any key nonce pair. So that would be, since it's 32-bit, that would be 2 to the 32nd power. But remember that each block is 64 bytes. So we would actually This is actually 2 to the 38th. Oh, that was terrible. 2 to the 38th power is the largest amount of data that we can do for any key nonce pair. And that is a large number. So that's 256 gigabytes, kilo, mega, giga. So we'll just say and then lastly, there's no authentication. So if we had data somewhere and the bits are like this, and then an attacker comes through and let's say they had access to the hard drive or they have access to the operating system and they change a bit like this. ChaCha20 has no native inbuilt support for or helping properties for that case. So we would have no idea that that changed. We will get corruption, but we will not actually have any idea that that changed. So we need some kind of authentication, which is why we're moving towards the XChaCha20 Poly 1305. But for the ChaCha20 cipher itself, there is no authentication. So we need to be aware of those things when we're designing our API implementation. We need to be careful about 32-bit counter. We can't do anything natively here about the authentication. That's going to come in later. And the key plus nonce pair is very difficult because the key and nonce are caller provided. So we need to be really clear about who owns that security expectation. So for C, there's kind of a different class of things, right? So C compilers, they only see pointers, integers, and loops. They don't know anything about security properties or anything like that. Well, currently, there might be smarter compilers in the future, but a pointer and length from a caller is just a promise. So if the caller is wrong or dishonest, then they can cause all kinds of issues. So we can have out of bounds reads and writes. We can have undefined behavior. The input, so if the caller gives us input and output, it may refer to the same memory. But if there are partially overlapping buffers, then we may overwrite plain text that we haven't read yet, leading to data loss. The C integer behavior is not automatically cryptographic behavior. Our counter is an unsigned integer, so wrapping is defined by C, but ChaCha20 won't allow it. So we need to ensure that that doesn't happen. Bit operations also have preconditions, so a rotate implemented with shifts is only valid for counts from 1 through 31. So shifting a 32-bit value by 0 or 32 would be undefined behavior. Our round functions uses fixed safe count, so this helper should not be a general public API. And then finally, we may end up fighting the compiler because we do some things like memset to 0, and an optimizing compiler may decide that this is unnecessary. We're not touching the value again, so it's left there. But what we don't want is, so, you know, you have you calling this ChaCha20 function and having your key be in your computer chip's RAM somewhere. And then Mr. Evilman after you get up and walk away is able to see the bits left on the system or in the RAM. So we want to wipe all that to 0, and a compiler may find that unnecessary. And then we need to look at our API. So the first thing is who owns nonce randomness or uniqueness. So a function cannot remember what's been called before. So this needs to be on the caller. So we are not responsible for ensuring the nonce is unique. They would use a random number generation function and they would just apply that. The who owns the counter allocation would be the caller. So counter is the caller. So the person calling this function is responsible for ensuring that the key and nonce pair are never overlapped. The output size is going to be the caller because they need to make sure that there is a big enough output buffer for what we're encrypting. So if they encrypt 128 bytes of data into a 64 byte buffer, that we can't do that as a function. We can't stop them from doing that as a function. So making sure the key material is both secret and valid is going to be on the caller. Validation of arguments, so that's going to be us. So for example, rejecting null pointers when a non-zero length requires them, and rejecting impossible counter ranges, that's going to go on us. We're going to call that we're going to call ourselves XCP here. So validate arguments is going to be on XCP. Never writing output after any detected validation failure is going to be on us. So validate before processing is going to be on XCP. It's going to be on us to make sure that in-place Zorin works. And what I mean by that is if you basically have a block in memory and this is where your current data is and where you want the encrypted data to be, giving us that exact same input output block in length should be supported. So that's going to be on us to make sure that that's correct. And then we're going to say checking return values. What is that? Is going to be on the caller. So we can say if something went wrong, but it's going to be up to the caller to make sure that they're checking for what it was and handling that situation appropriately. All right, so next let's work on implementing the Cha-Cha 20 preventions.